Welcome back, quantitative analysis students. This is Mr. Marquetta, and I'm here to deliver your final lesson, which is about integrals involving exponential and logarithmic functions, along with the definite integral, where we include limits on the integral. And after we're done integrating, we use substitution with two constants and subtract. Today, I'd like to show you some examples using the sideboard, and we'll be writing today to show how that works out. Let's take a look at some of these examples. First, recall the idea of what it's like when you take derivatives when it comes to exponentials and logarithms. E to the x, the derivative of e to the x was e to the x. So the integral of e to the x is e to the x. And I want you to remember it that way. It's really very easy. What is the derivative of e to the x? It's e to the x. So then what's the integral of e to the x? It's e to the x. And then the other thing that's important that we have to talk about is when you apply the power rule of integration, in the case where n equals -1, we come up with an issue with dividing by 0, and that's how the natural logarithm comes about. I want you to take a look closely at this with me. This is the first idea I was trying to share with you, which is that if you have a function that has e in it, e to the x, the integral of it is going to be e to the x. That's what we mean here. And further, if you have an expression up here and you are multiplying by its derivative, you can apply that concept of the u substitution and the chain rule that we did yesterday with some other examples. But ultimately, the real story is the integral of e to the u du, or e to the x, is going to be, of course, right back e to the u. Now, the other important thing that we're learning about today is the opposite. Instead of exponentials, we're talking about logarithms. Why don't you take a look at this example? In here, you'll see that we're doing, you could apply the power rule. We do have u to the -1. But think about that for a minute. What happens when you do u to the -1? If you're taking the integral of u to the -1 and you try to apply the power rule, you get a division by 0 error. Let me show you what I mean. Okay. So what we're going to do is talk about what it means if you have -1 as your n using the power rule. So if you were trying to find the integral of something and it had x to the -1, you might think immediately to use the power rule. Remember that the power rule says that if you take the integral of x to the n, it's going to be n plus 1 as the power n divisor. So let's do that here. In this situation, x to the -1 plus 1 over -1 plus 1, look at what we get. We get x to the 0 over 0. And what happens when you divide by 0? I've been telling you this since the 4th grade, right? You can't divide by 0. In other words, there's no solution to this question. In other words, you cannot apply the power rule to this. So after a lot of empirical investigation, we've come up with, using limits and using cases that are very close to -1 for n, we have this new statement that when we try to figure out what is the integral of x to the -1, it's going to be the natural log of x. And we put absolute values around it as well, just in case x is negative, because for negative cases it still applies, but with logarithms you need to have positive arguments there. This is a model that we're going to use along with this other model involving e to the x, which e to the x, like I told you, is very simple. The answer is just e to the x again. But when it comes to doing an integral of anything to the -1 power, which by the way also can be written this way, 1 over x dx, that is also 1 to the negative power. Just remember that that translates into, according to this definition, the natural log of the absolute value of the expression. And then, of course, you could apply the chain rule to this and do the u substitution in cases where you have 1 over an expression, not just x, but an entire expression, if you also see near it the derivative like we talked about earlier. And that's what you'll see in today's examples. So let's see if we can get through some of those cases. Okay. The first one I'd like to focus on with you, I'm not going to write, I just want to show it to you. Here's example 1, and right underneath it, example 1, you see the solution. Notice that they're doing the same thing that we've been doing over and over again. The first step there is to pull the 5 out. That is the coefficient rule of integration. So the 5 is written again there as if it were outside of the integral. I'm talking about this part right here, how we change this into this, taking the 5 out like this. So whenever you have a constant in there with the integral, you can pull it out like we did here. And now we have the age-old question, what is the integral of e to the x? And of course, that's just e to the x, which is why your solution is this. And then of course, don't forget to add plus c, because every time you do any integral, you always have plus c. In fact, these models right here should have plus c in them as well in our chalkboard. All right. So that being said, the rest of these are all straightforward examples that involve e to the x and the natural log, and they also involve a u substitution. Let's work on those on the chalkboard. So the first one, it may be a little intimidating to see that there's an exponent with an exponent. Welcome to calculus. That's an average thing in your homework you'd see. But I do notice that this exponent up here, it does have a derivative that is right here. And I need you to look at these integrals kind of at like through a spyglass, trying to figure out what that key to the lock is. That's the puzzle here. If I move this around just a little bit to look like this instead, now I have the differential there, and I can apply the u substitution idea, which is let u equal the thing that you're trying to replace with x. We're used to e to the x, but this is e to the something else. I'll make u that something else. It's x squared. Now, what is the derivative of x squared? It's going to be 2x. So the way you write it is du equals 2x dx, which is right there. So if this is u, and this is du, then this whole statement just became the integral of e to the u du, which is very simple. It's just e to the u. Last but not least, what was u? We stated u is x squared. So now the final solution is e to the x squared. And don't forget, since it's an integral, plus c at the end of every integral. All right. Example 2 is a great model to show how it's really right there. You don't have to look very far. You see x squared and then you see 2x. They're connected because one is the derivative of the other. And that's what you got to look for in these kinds of questions to get them right, is to be able to figure out, looking at it, if you have one expression like this, such that you see the derivative of it somewhere else, and you can come up with this idea. Right. Another example is just like that. In this case, we do have something on the bottom there, and that might feel a little bit uncomfortable, but remember what we did in the past when we had fractions like that. We just used negative exponents. You could do it that way. Let's say, for example, and this is where you have to get a little creative and try to experiment and say, well, what if I let u equal x squared? Then what happens? Well, then the derivative is 2x. I kind of don't see 2x anywhere. What if I let u equal x cubed, like the exponent of e? Well, the derivative is going to be 3x squared, and I do see x squared there. And after you think about it a little bit, you might come up with the scheme that maybe u should equal x cubed. Follow through with it and see if it works. That's the trial and error of these kinds of questions. And as you can see, it could be very frustrating because it's complicated writing and it's advanced ideas in mathematics like exponentiation and logarithms and such. You might feel tempted to think this is going to be a natural log just because of the way it looks with the fraction, because our other model that we talked about earlier had to do with 1 over x, and that turned out to be the natural log. So anyway, the point I'm trying to make, friends, is you do have to experiment. You don't know necessarily what it is. In this case, your best approach would be first to rewrite it so that e to the x cubed was not on the bottom, but instead had a negative exponent. I would write that like this. Now the integral of e to the negative x cubed x squared dx. Okay, and then the next thing I do to get us straightened out here is I'd say u equals that exponent. So if u equals that exponent, then it follows that du equals negative 3x squared dx. And I do have x squared dx, but I don't have negative 3 there. So the way I deal with that is I solve this equation for just x squared dx. meaning I'm going to need to get out that -3 like this. I have a new statement now that says -1/3 du equals x squared dx. And now I have license to put this expression in place of this one, like that. Further, of course, we stated that u is this, so now this has become u. Let's rewrite it, and it suddenly becomes really very simple. It's now the integral of e to the u times -1/3 du. So just like the last lesson we did, it always boils down to a very simple thing that is obvious. The integral of e to the u is e to the u, and then you come back and put u in there. In this case, you have that little bonus of that constant, and we saw that yesterday in some of the cases where we were doing integrals. But ultimately, that is just a multiplier, so we can pull it out like this: -1/3 integral of e to the u du. And now that is, of course, -1/3 e to the u. And e to the u, we know u is that expression. So it's -1/3 e to the x cubed. But don't forget plus c. And this is the answer we expect for a question like this. Now, before we go into the next part, I want to give you a little bit of a background with fractions, because I know that fractions are not everybody's strongest suit, but there are some little things about fractions that if you can get comfortable with these little ideas, then as you carry on doing integration, when it's time to deal with fractions, you'll feel like you have a little bit of an advantage. Here's something that people don't realize about fractions, that if you could just realize it, a lot of these questions become very simple. If you have, for example, something like du over -3, that's a very ugly looking expression. It's kind of odd, but there are a lot of expressions that are exactly equivalent to that. You could have made that this. You could have made that this. You could have made that this if you wanted to. If you want, you also could have made it this. All of these expressions, all of the same quantity. Out of all of them, this is the most appropriate one if you're giving your final presentation in mathematics for an answer. So when you see this, you might elect to simplify it to look like this or to look like this for whatever reasoning you have, whether it be that maybe -du equals dx or some other reasoning, which is fine. But just know that if you want to really just be professional and go all the way with it, you should always be able to take any expression like this and convert these all into this. There's something really nice looking at a fraction that has a big negative sign and a fraction line that are equal. It's uncomfortable when you look at something like this or something like this, and you're not sure if it's a minus or not. This is very, very clear that it's -1/3. So when we were doing this example, oh, here it is. When we were doing this example, when I got to this point here, I automatically changed that right into this. And I did that because I wanted to have it very, very clear what this quantity was, because I have to replace x squared dx with it. And notice when I wrote it into the integral, I made it very clear that I mean this whole thing. If I made that minus sign small because I was not less than confident about it or something, it would make things a little more challenging. That's why I'm just trying to stress to you, when you do these integrals, you have to be deliberate, and especially when it comes to fractions like this, you really have to go the extra mile and make them very clear, because there are many fractions and it becomes a headache. If you just get used to doing it perfectly every time, it'll become, it won't slow you down in what you're learning about integrals. That being said, here's another case of a fraction. Let's see if we can use what we learned in that situation to get some answers to this. You may notice that there is a common factor of 4 amongst all of these coefficients of everything in here. So you might want to do something like that. I recommend, instead of crossing them all out, you should really show factoring. If you factor the denominator, you would be using GCF factoring, meaning the largest quantity that divides into both of these. For 4x and 8, that would be 4. So I could write it as x plus 2, and then I'd have 4 on top. And then, of course, the 4s would cancel out. Please don't hesitate to do some algebra before you do integration. Sometimes they give you an expression that is clearly simplifiable, that you could simplify, and you should simplify it if you can. because it will only make things quicker and easier. Now, this one does follow the model that we're familiar with of finding the integral of 1 over x. Let me get that back out for a minute. There it is. So when we were talking about this, remember, the integral of 1 over x is going to be the natural log of the absolute value of x. Now, I don't know 1 over x plus 2, but I do know 1 over x. However, it's kind of interesting how if you let u equal x plus 2, I'm going to put a square around 2 because we're going to come back to this number 2 for a minute, okay? And now I find the derivative of this. On the left, I have du, and on the right, I have 1, because the derivative of x is 1. And then I have the derivative of 2, which is nothing. So I have 1 dx, which means, in other words, du equals dx. The reason I put the box around the 2 is because what if that number wasn't 2? What if that number was 71 or 688 or 3.14 or -5/8? Wouldn't it still be the same? Because that's a constant. So I want you to remember this structure here, friends, okay? 1 over x plus anything always boils down this way, that you wind up making it look like this, the integral of 1 over u du, which is, of course, the natural log of the absolute value of u. And then you go and substitute into u this expression, and your final solution is the natural log of the absolute value of x plus 2. But then don't forget your plus c because it is an integral. All right. Now, if you didn't notice in the beginning that you could do factoring to remove these 4s and to reduce this fraction first up, that's okay. You could have gone in and said, take the 4 out and let u equal this, and then do the derivative, and it still would have all scratched out like fractions and canceling out. It all would have boiled down again, right, but it would have been like the long way. And you could do that if you want, but often in calculus, it's really strongly recommended that before you go right in with the operation, especially if it's integrating, that you see if there's any little quick algebra tricks you can pull off first. All right. All right, carrying on, now we have another one here, and in this one, we have a denominator that's quadratic. What that means is that since the bottom has x squared, the derivative of something that has x squared is going to have something that just has x in it. Remember, the degree kind of goes down because of that n-1 thing in the derivative rule, which is why it feels like it's most likely that somehow the derivative of the bottom is connected somehow with this numerator x minus 3. Let's just jump in with both feet and let's let u equal the bottom and see what happens, especially considering that I'm comfortable with this natural log formula where I have 1 over something gives me the natural log of the absolute value. It's a fraction, it probably will be like that too. So I'll start by stating that u equals that denominator x squared minus 6x plus 1. Follows now that du equals that derivative, which is 2x minus 6. And don't forget dx. Now, a word of caution here when you're writing, make sure if you have something like this, you don't mean dx times just -6. You mean dx times this whole quantity. You have to use parentheses there. If you don't, you're going to be a little bit off. But by the way, here we go again with our old algebra skills. Isn't there a factoring available here? You can pull 2 out of both of those terms. So make it 2 times x minus 3 like this. And then suddenly, I recognize this quantity. It's right here. If I want, I could take this dx and put it right here instead. And maybe what I need to do now is collect this by dividing out the 2. This is very much like before when we were talking about -1/3. Here I have du over 2. I'm going to call it 1/2 du. I'm going to say that's equal to x minus 3 dx, which means I can replace this entire numerator with just 1/2 du. And I can replace the entire denominator with just u. That would make it look like this. 1/2 du over u. Suddenly, it's really very simple. Remember that this formula here, you can write this to look like either the integral of x to the -1 dx, or you could call it the integral of 1 over x dx. Or if you want, because of all the things we learned about fractions, You could call it the integral of dx over x. It's the same idea. All three of these become this expression, the natural log of the absolute value plus c. So this one right here is what I'm thinking of when I'm doing this question, because as you can see, that kind of came up here. And now I could just use the constant rule, not the constant rule, but coefficient rule, which means take a half out. Rewrite it looking like this: 1/2 integral of du over u. And then, of course, that is the 1/2 times, now the integral of du. That's the definition of the natural log. Natural log of u is the integral of du over u. So that means I'm going to write here the natural log of u. And what is u? U is this quantity here. So one more writing: 1/2 natural log of that expression, x squared minus 6x plus 1. Close the absolute value, and don't forget plus c. Because when you integrate, you have to put plus c in there. And that's example 6. Okay. Piece of cake, right? I know it's very complicated, friends. I hope that you feel comfortable with the material. Please let me know if I could explain it any more, or if you want to go through any other piece of it. It is really ultimately just old algebra stuff, except for this little piece where you start trying to fit the question into one of the models. This is one of the models that we use today. All right, so before we go into the next chapter, there are a couple of applications we have to go through. Let's talk about those. Most of the time with these applications, even though they're a little bit challenging to kind of grasp because they're about pretty specific fields of science, it still kind of tells you explicitly, now do the integral and then plug this in, like at least it kind of tells you. So you don't have to really be a physicist or in this case, a finance real estate person to be able to get your answers. It kind of does really tell you what to do. Let's read example 3. It says, suppose the rate of change of the value of a house that cost $200,000 in 2015 can be modeled by, and we have an expression there, and it's an equation that looks like a derivative. It's a derivative in terms of E. We've got E in there, and we have T in there for time. Then it's telling you V is the market value of the home in thousands of dollars, and T is the time in years since 2015. So find the function that expresses the value of V in terms of T. Now, I didn't have to know anything about real estate or inflation, but if you gave me that equation that says dV dt equals and all that, and you want V, I know I have to integrate. I just integrate both sides with respect to T. Then when it's done, it says, now find the predicted value in 2025. Remember, we talked about aligning the data. In this case, we are telling you that T is the time in years since 2015. So if you're asking about 2025, that means T equals 10. And so it's on you to know to plug in 10, not 2025, but 10 into the value of T after you take that integral. So in this question, you'll notice, unlike our last couple of examples where we had simple statements like x cubed plus 4 and e to the 5x, now you have strange coefficients, 15.4, 0.077, and they're only there to show a real world example of the kind of models that are used in these fields. For example, in real estate inflation, this is most likely a very accurate model, and they probably did a lot of empirical work to get it to be just that particular coefficient for each of those two places. How would we solve this? Well, we would follow the same rules we had before, but we might find ourselves doing some weird calculations with these odd coefficients. So let's take a look at the solution. What I did was I copied and pasted the solution out of the textbook here so we could look closely at it. Instead of having to write it, I thought we'd just kind of work through it together. You'll notice that what they did first to solve this integral is they took out that coefficient 15.4, which is, we've done that before with simpler coefficients, but you take that out. And once you take that out, you kind of ignore it and act like it's not there. And then you're in a position to be able to focus on all the rest of this, And then what they did was, to get creative, they changed dt into all of this. And the reason why they did that is because they let u equal 0.077 t, and then du became that. As a result, the fraction that you see here came out. This is very much like when we showed you negative du over 3, or in our most recent example, it was 1/2. Here, it's just an ugly large number, but it still is the same concept, how you would divide both sides by it to isolate u or du to be able to get your new coefficients. As a result, on the left, you have to do a strange multiplication, 15.4 divided by 0.077. Take a look at what the answer of that is. It's 200, which is kind of a little bit odd. It's almost as if they deliberately selected those two numbers, 15.4 and 0.077, so that when you did find yourself multiply them, it gave you a nice round whole number, 200. It's almost a hint that you're on the right track. But you'll see when you do your web assignment practice, friends, that they set up the questions like that, and that there's a clean, easy answer. And then later on, when you have your solution, which in this case is the line there, v equals and that whole quantity, when you have to put your numbers in, it's a piece of cake because the number is not ugly, it's 200. So let's move on and look at the next piece. If we use v equals 200,000 when t equals 0, and that's what's happening in this case because we told you here that in 2015 it was 200,000. That means that you should assume that, and let me be really clear about this because this is a little tricky. That means that you should assume that if you have the original function v equals, that there is one point on that graph, and the point has a 0 in it, and it has a 200 for the other value. Meaning that at the beginning, at time 0, which is your independent variable or the x, the answer of what is the cost of the house was 200,000. So we can take this equation here and the position of the t, put a 0. If you put a 0 there, 0 times 0.077 is 0, and e to the 0 makes a 1, which means that that makes this whole thing just 200. That's why you see 200 here. You see 200 here because we told you that it was 200,000 at year 0. That's why it's 200, because v is in thousands. So you can solve for c quick and easy that way by getting it in a simple little equation like this. And when you find that c equals 0, from that point on, you can just assume that it doesn't have plus c. Really, the formula is just this piece only. If you found out that c was 20, it would be that plus 20, or if it was 91, it would be that plus 91. But because of the original question, which stated that at the beginning in 2015, when we were at year 0, the value was 200,000, that tells you that after you integrate, when you have a statement like this, you can swap out 200 into v and swap out 0 into t to go and find out what c is. Why do you want to find out what c is? Because you want to have an equation in terms of v and t only, not c. So you have to go find c, and that's part of the application. Friends, I want you to get comfortable with that. That's a normal part of the application. In the other examples we've done up until now, they were just mechanics. They were just mathematical questions. There were no applications involved. So the answer was abstract already, and you have to add plus c, so that as a reminder, when you do an application to it, that c is a number we don't know that you got to go and find if you want to further pursue the idea of this integral. For example, in this situation, you could find c knowing what the value was at the beginning of the story. At year 0, the value was 200,000. That implies that the constant c is going to be 0. So anyway, you have your answer of what v is. It's a good example. And now you want to find out what happened at 10 years, right? So if you're trying to find out what happened at 10 years, you're going to take this equation that you just found for v, and you're going to plug in 10. That's what we have here. It's the same equation, but notice there is no plus c because we have determined that c is 0. So the full equation looks like that, plus nothing. We put 10 into the position of t and get a calculator, and 431.95 is the answer. But remember, we are giving v in thousands. So 431.95 thousands means to move the decimal point in 3 spots to the right, just like this. Here's the decimal point. Go 1, 2, 3. That's the reason why we have an answer that looks like this, 431,000. If you don't put that in right, it will be marked wrong, and you have to be very conscious of that as well. So when you're getting ready for the exam on Monday, make sure when you look at the exam review that you follow all of those steps in the tutorial to make sure that you're getting C correctly and that you're coming back, and also that you're putting your numbers in according to aligning the data correctly. V is in thousands. That's easy to throw us off. All right. All right. So that's one application. We do have one more, and then we'll take a short break before we go on to the last section. Okay. This one is about population growth. Because the world contains only about 10 billion acres of arable land, world population is limited. By the way, that word arable, A-R-A-B-L-E, arable land is land that can be farmed or land that can be used to grow produce, or fertile land that is suitable for farming. That's what arable means. And I had to look it up because when I first looked at this, I wasn't that familiar with that word. But what they're talking about is the sustenance that that carries on so that we can keep on with the human race. Suppose that world population is limited to 40 billion people, and that the rate of population growth per year is given by this formula. Now look, we have a similar formula to last time. It states a derivative equals, and we have an expression, dp dt equals, and we have k, 40 minus p. We have 11. We have three variables here. Notice that they're funny variables. One of them is capitalized P. When you're doing your WebAssign homework, it's going to be marking you wrong if you put lowercase p or if you put capital K. If you find that that happens when you take your exam, please notify me and I'll give you credit back, because it is a very slight mistake to mess up the capitalization of these, the way that they make them. But just be conscious of that if you're not getting something right on WebAssign, it just might be because you have something capitalized or something like that. Anyway, here's a great relationship between P and T in terms of a derivative. P is going to be the population in billions at the time T, and K is a positive constant. Now, I don't know what K is. K might be negative 0.077 like it was in the last one, but for all intents and purposes, K behaves as a constant. So that means that if you take the derivative of K, it's 0. If you have K times X, the derivative is K, and so all the other rules that apply to constants apply them to the letter K. So keeping that in mind, next we have then the relationship between the year and the population during that year is given by this integral, and we have another statement that is talking about an integral and is also telling you that the denominator 40 minus p is greater than 0 because 40 billion is the population's upper limit. Look at directions for part A. Evaluate this integral and find the relationship. So that was a beautiful story, but if you don't really quite understand the whole story, that's not a big deal because it's telling you, okay, do that integral now. After you do that integral, the next thing it says is use properties of logarithms and exponential functions to write p as a function of t. Now that's a little bit of a strange way to say, please write it as p equals, okay? So it's gonna be p of t equals or p equals, and what you have after that is only numbers and t's. You might also have k's because k's are constants like we said earlier as well. So how would you go about doing this? Well, again, since the numbers are odd, I copied and pasted the answer right out. I figured instead of writing this, it's here, and let's take a look at it. If we're trying to do this integral, I'm going to act like 1 over k is also a constant, because for any constant, its reciprocal also represents a constant. If I'm trying to do 1 over 40 minus p, maybe it would be smart to start with making the denominator u equals 40 minus p. Then I could start following the idea of making a natural log out of it. If I say u equals this denominator right here, then it turns out that du equals negative dp. And furthermore, negative dp equals du. So any way you want to write it, in any different way that you want, you can put a negative there and a negative here to compensate. Ultimately, you wind up with 1 over this, or 1 over u, which is the natural log of the absolute value of it, and then there's a constant. This one, if you take a pencil and paper and try to do it, it's really actually just the same question we did recently, just with a minus sign in it, and with odd letters like P and K and such. For example A, it should be a little bit straightforward, and notice we don't know what the constant is, so we're just saying C. For part B, they're asking you to solve it in terms of T, meaning say that it's P equals. So here's how they do it. We have the statement T equals this, which is what we just found, right? And since 40 minus p is always greater than 0, that means that this is always equal to this. So in other words, it gives us license to be able to take off the absolute values. And whenever you see a statement like that, where they tell you, by the way, that denominator is greater than 0, which you will see often in your studies with WebAssign, what that means is that when you're done with your answer, you have license to take those absolute value bars out. Because if it's greater than 0, then why put absolute value bars on it? If I tell you a number and you know it's greater than 0, I might as well have just told you the number. You don't have to do the absolute value. It's the same as what it will be. So anyway, that's why they're carrying on about how something is greater than 0. Next, it says solving this equation for p requires converting it to exponential form. So if you're very careful about it, you could manipulate this equation to turn into this equation that you see right here. And it does involve that concept of going back and forth between logarithmic form and exponential form. Let's take a look at that for just a minute before we carry on. Okay, friends, have a look at this now. Remember how we talked about going back and forth from logarithmic to exponential? In the case where you have a log, the base is right here, and then this is actually the power. And then the answer is right here. This is the exponent. So if you want to take those and move them around, the a winds up being up here, the b winds up being the base, and then of course the n winds up being the other side. In the case of natural logs, it looks like this. The natural log of x equals y. That's the same as e to the power x, e to the power y equals x. Right. So both of those connect, and that's something that we should kind of already have in the back of our minds. We should already kind of know that. But yeah, when you see something that's logarithmic, you can move it around into exponential, just remembering this relationship. And that's what they're talking about in the solution to this question. So let's take a look back at that now. And then after they do that, they do a little, they take this and they go into the other direction with it and make it this. And what you have here is a little bit of an exercising of exponent rules and how you can use multiplication and addition in funny ways with exponent rules. But after a little bit of work, you could solve it for p by just now subtracting the 40 and multiplying out the -1, and you'll have it for p. So what you're looking at is really just an exercise in algebra. You're using larger than usual expressions, more than one variable, more than two variables. And please let me know if you need me to go through any of these with you. I'm happy to go through it on the chalkboard. If you have any questions, we can do them together on Monday before your exam. Just let me know. Send me an email. I'll be happy to work with you on it. All right. We're going to take our break here because the next part of our lesson actually is going to involve the fundamental theorem of calculus, which I'll leave here for you. It basically states that when you have an integral and you're about to have limits, you first integrate, which is what you see here. And you'll get what the answer is after you integrate. And then when you're done, you'll take this b and this a and substitute it into your answer and subtract them as follows. This is just an application of all the things we've already learned. So it's basically nothing new except for the little bonus of when you see the numbers, put them in and subtract in this particular way, and then you'll get your answers. We're going to do those examples all on the chalkboard. I have them all written out and ready. But first, we'll take a short break. Right now, it's 5:21. I asked that we return at 5:35, and at that point, we'll carry on with the last section of quantitative analysis 2, which is chapter 13.2, the fundamental theorem of calculus. Okay, friends, so we'll see you in just about 15 minutes. 5:35 will return. Thanks for your attention. Welcome back, students. Okay, so I left that there. I hope you had a chance to take a glance at it. That is the fundamental theorem of calculus. And it states that if you're taking the integral and you have limits, first integrate, that's step one, then evaluate, which is to put the two limits in and subtract into the answer that you got. Before we go on with this, I do want to share with you, as I always do with my students, when we get to the fundamental theorem of calculus. As you can see, this is really the culmination of everything you've learned all this time, with limits, with derivatives, with the derivative shortcuts, and then with integration. And now you're finally in a position where you finally are in a place where you could learn about the fundamental theorem of calculus. In mathematics, there are three fundamental theorems. The first one is the fundamental theorem of arithmetic. It states that any composite number can be written as a product of primes. The second one is the fundamental theorem of algebra, and it states that any equation of degree n has exactly n solutions. That's the fundamental theorem of algebra. The fundamental theorem of calculus, behold, here it is, with the integral in it in all its glory. It's absolutely hideous. Let's apply the fundamental theorem of calculus now to get some answers to some of these funny, quirky questions. You'll see that, again, we're going to have a greatest hits of the logarithm and the power rule and all of those other fun things that we've learned so far for derivatives. But we're going to add on there the idea of having a limit because it's a definite integral and getting an answer. Now, note, if you did go in and put plus c in there, when you subtracted at the end with the two numbers, the 4 and the 2, or whatever the two numbers are, you would wind up also including c minus c, which would mean that the c would find itself to be kind of moot. Like it would not even matter what c was anyway, because it would be subtracted out anyway. I'm going to illustrate that after we do example 1, where plus c would have been. Okay, so let's do example 1 now. I have examples 1, 2, and 3 prepared for us to study. So let's take a look at it on the chalkboard. Here we go. And this first one, the way that we should do these is we should first act like they don't have limits, like it's not a definite integral with numbers, but just like if it was an integral, what would you do? The way I would deal with this is I would apply the sum rule first, which states that I can split the integral into those two quantities. And for now, I'm going to just ignore the numbers. I'm not going to put the limits on there until the end. Then I can do this because I remember from this one, I could apply the product, the power rule, which states that the integral of x to the n dx will be x to the n plus 1 over n plus 1. That means this ought to be x to the 4 over 4. And then this, I could pull the 4 out and put that in the think cloud. Right? And there was a rule that we learned earlier that said that the integral of the d of x is just x, right? So that means that this is really 4x. And now what we're going to do is evaluate. So everything that we just did, we've already learned all that stuff. But now we're going to start doing the idea of the fundamental theorem of calculus, which is where we're going to apply these limits and evaluate them. Here's how you do that. You start by, after you're done writing your answer of your integral, which is what I have here, now give it a big solid line like this and put the limits on the line like this. What that means is, okay, now here I go. I'm about to put 4 in and find out that quantity, and then write minus, and then put 2 in and find that quantity and do my arithmetic and get a final answer. So that would look like this. 4 to the 4 over 4. Try not to crack up. Look at how they make this. Look how ridiculous they made this. This is so silly. It's all 4s, right? And then that would be the first one, right? And then we would say minus, and then put 2's in there. 2 to the 4 over 4 plus 4 times 2. Now, what you're looking at here, friends, is just a little calculator fun. It's really quick and painless. This is going to be 4 cubed ultimately, which is 64 plus 16. You could do it in your head. 8, 9, 90. So the first one is 90. And then this one here is 16 over 4. That's 4 plus 8. 4 plus 8 makes 12. 90 minus 12 is 78. What is the answer to this question? It's not this. It's this. This is the answer because this is a definite integral. And definite integrals with numbers have an answer that is a number. And you want to show your work. But what is the final answer? It's that actual measurement, that number. All right. Now, for a minute, let's pretend that plus c was part of the story. Okay. So instead of having this, it was this plus c. Okay, I'm putting plus c in there. Imagine that this thing had plus c in it, and this thing had plus c in it. Can you see that this minus would distribute to the plus c, and they would wind up ultimately canceling out? It would be like this. So then they would go. So the plus c kind of just evaporates that way. Okay. There is something else I want to share with you that is a practical application of what this means before we go on to example 2. In this case, talking about x cubed plus 4. Now, x cubed plus 4 is a very specific function. Let's get it back. Try to do x cubed plus 4 for just a minute. All right. Okay, so x cubed plus 4 is going to look like this. Something like that. All right. And if you think about that place from 2 to 4, this is 2, and this is 4. And you consider this particular area that is enclosed right here. This is the idea that if this is y equals x cubed plus 4, and these are the limits of 2 to 4, if you integrate x cubed plus 4 from 4 to 2, like so, it'll give you that area. In the same way that we apply the idea of the derivative to be the slope of the tangent line to a curve, we apply the integral to represent the area under a curve. And if you include the limits from the fundamental theorem of calculus, like 4 and 2 in this case, then you're talking about this red area that I shaded in, because at x equals 2, there's a line here cutting it. At x equals 4, there's a line here cutting it. The y-axis itself is a line cutting it. And then you have the curve itself that is x cubed plus 4 in the funny shape it makes right there. This specific area can be found exactly to be 72 square inches exactly. That's the idea. Now, this is actually way farther up. That's why it looks like it's so much less. But if you were to graph this, it really would look something like this. And that's why the number is actually 72. This is really more like 10 squares, but it's 72 squares. And you know, if you graph it, it doesn't look really going out that way. It goes up a lot faster. And the point I'm trying to make is, friends, when you actually find an integral with limits like this, it's the equivalent of finding the area under that curve from x equals this to that between the curve and the x-axis using those boundaries. So you'll probably see that in web assignment with your practice. That they have some cases of here's a function, the limit from this number to that number means something, and it's a great application from geometry. And it also is a really unique and fun way to find areas of very strange figures. So for example, if you know the formula for the area of a circle or the area of an ellipse or any other funny shape, you could put in there and you could find areas of weird quantities of weird functions with specific limits and use that integration to get your solutions. All right. So anyway, just wanted to make a mention of that because this one is our first case of the fundamental theorem of calculus, and it is a little bit more easier to grasp, especially on a graph, if you could consider it. So let's move on to the next one. Example 2, we're going to do it again. This time we have different limits. We have 3 and 1. I'm going to apply again the sum rule and start by rewriting this to look like this. Don't forget to put dx next to everything that you do with the integral. Anytime you write an integral, you must write dx somewhere to finish what you were writing. Also, that is the sum rule. Let's now apply the coefficient rule, which gives us license to pull a coefficient out of the integral like so. 3 times the integral of x squared dx plus 6 times the integral of x dx. Just to make things easy on myself, I'm going to include that, by the way, that is x to the 1 over there, because I'm going to use that when I apply my power rule. Remember the power rule? Here it is once more. The integral of u to the n du is going to be u to the n plus 1 over n plus 1. Last time we wrote, I think we used x. You could use p or anything you want. In the book, they use u a lot, so that's what it looks like with u, but it's the same idea. Meaning, take the exponent and add 1. When you add 1, that's your new exponent, and it's also your new divisor. So in the case of n equals 2, this becomes x to the 3rd over 3. Don't forget that constant coefficient multiplier outside over there. Same thing here. In the case of n equals 1, this becomes x to the 2 over 2. But don't forget that multiplier of 6. If you forgot, when you're multiplying a fraction times a whole number, you can make that whole number over 1, like this. And then it becomes clear that this is happening, and this is happening. And you're left with just x cubed plus 3x squared. Now, we'll stop there for a minute because we already learned all that stuff. Today's lesson is about how to apply the fundamental theorem. So from that point on, if you want to apply the fundamental theorem, what we'll do is we'll draw a large solid line to show that, hey, here we go. We're about to do our substitution. And we're going to use 3 and 1. So it should look like this. It should look like 3 cubed plus 3 times 3 squared minus 1 cubed plus 3 times 1 squared. You could do that in your head, right? This is 27, and 27 is 54. And this is 1 plus 3, that's 4. This part, friends, is actually really very easy, and you can do it in your head. When you get this written out, you should be able to glance at it and use your college math aptitude to get 54 and 4. You should be able to get that part from there. All right. So if you were actually going to graph this function and look at it from the limits of 1 to 3, you should find that there are 50 units in there underneath that curve all the way down to the x-axis. For example, too, we have a great case of the sum rule here, and we're also using the coefficient rule here. Then there's good reducing cases here. And then when we're through, we show the fundamental theorem by substituting the 2 limits and doing a little arithmetic. Example 3 is very similar. But example 3, now you're starting to get into the puzzle side of it, where you have to experiment and say, should I let u equal x squared? What if I let u equal x plus 9? What if I let u equal x squared minus 9? And you start getting creative with different things you could use for you. And when you do it, if you go in the wrong direction, you'll find that it's very complicated and not working out. And chances are you probably have to go back to the drawing board. This one, the way to solve this issue is to first notice that I have a multiplier of x here. And by the way, that's very, very easy to miss. Let's take a look at that once real quick over here before I go on with this question. I want you to look at how subtle that is and how very easy that is to miss. I'm looking now at this question and how that x dx is so slight. You could miss it if you're not looking closely. I'm talking about this part right here. See it? If you don't put that x in there, then you really can't figure out this question. I want you to be really sensitive to writing like that. That you might see cases of it's easy to miss. They try to make, they even use exponents of exponents to make it look small, so it's hard to miss it. So in other words, think of it this way: don't let them get you. You know, it's calculus, so it's complicated, but you need to see through it. X dx being there makes me feel like I should use the distributive property and give it to each of these things, which is a little abstract. Usually with a distributive property, it's a simple little case like this. But this time the b in that model is a big ugly fraction, a big ugly root with a whole exponent and everything. However, it still does apply. You might feel a little tempted to let the x go to each of these two things, but you cannot, because the root is the same thing as having a parentheses with a power. You can't distribute into there, but you can at least distribute to these two quantities here. This is the first and this is the second. It's as if this was b and this was c. So if you did it that way, and we're going to ignore the limits for a minute, it would now suddenly look like this. X times x squared minus 9 dx plus 2x dx. In other words, the x was given here and here. Why would I go about doing that? Well, this is already in the bag. I know I could figure that out. That's a little aside. We're going to do that later on. But this one is the headache. Let's think about letting u equal x squared minus 9. It follows then that du equals 2x dx. But I don't want 2x dx. I want x dx. So I'm going to have to go like this. And now I think of it this way, 1/2 du equals x dx. So that means I can make it the integral of the root of u times 1/2 du. And then pull the 1/2 out like so. By the way, u to the root of u is u to the 1/2. And now when you solve that, it's going to get a little ugly. So you got to just be really careful with it. Let's do that. So I do have a 1/2 there. And I'm doing, first of all, I'm thinking about 1/2 plus 1. And that is 3/2. So it's u to the 3/2 over 3/2. So don't let this intimidate you. The best way to go about doing this is to just jump in with both feet and write it nice and large so that you don't get confused about what it says. Divide by 3/2 is the same as times by 3/2. So I'm going to rewrite this now to look like this. And then that 3/2 really means 1/2 times the root of u cubed times 2 over 3. Then I can cancel these out. And now I have the root of u over 3. By the way, what was u? U is x squared minus 9. So now that is the root of x squared minus 9 over 3. The last piece here is we're going to make sure that we now finish up this. I'm going to leave that for a minute. Leave that right there. We're going to finish up this. 2x, you might recall, the derivative of x squared is 2x, so that is ultimately just x squared. I'll put that here. Sorry, x squared. And if you wanted to, you could have done it this way. You could have said, we'll make it 2 integral x dx, and then that's x to the 1, so it's 2x squared over 2, which is going to be just x squared because of that. So now, we have to also integrate it using these limits, 5 and 3. So the last step here is to take this expression at 5 and 3. So if I put 5 in here, I get 25 minus 9 all over 3, and then plus 5 squared. That's going to be 16 over 3 plus 25, which is 4/3 plus 25. Next, if I put 3 in there, it becomes 3 squared minus 9 over 3 plus 3 squared. And doesn't that become 0? And 0 divided by 3 is 0. So 0 plus 3 squared is just 9. So what that means is I have this quantity minus 9. That would be now 16 plus 4/3. And you could make that 17 and 1/3. And you could make that 52 over 3. Any of those expressions will work for this answer. So that one was a little bit ugly, right? But I hope that makes sense. This was first using the distributive power, the distributive property to distribute the x through, and then handling these separately. This becomes a menace. Just keep an eye on it. Make sure you get it in there, x squared. But the x is there, and we result in a 1/2 du to get that to work. And then you have this nasty 1/2, and there's all these fractions. And if you're very careful, it boils down to root u over 3. Then recall that u is ultimately x squared minus 9. So this is now u cubed this is now root u over 3. It's root this expression over 3. And don't forget that plus x squared. Now we're going to evaluate 5 and 3 because the original integral was a definite integral from 5 and 3. And we'll put 5 in, and that's all this arithmetic. I get this expression. We put 3 in, and I do all this blue arithmetic. I got 9. You subtract them, and you get this quantity. Okay, there are some specific rules that are really straightforward and easy that you can kind of take for granted, but we have to kind of prove them to you so that you can lean on them. For example, if you consider that the limits are equal, like you see in part A, then the answer should be 0. If you consider these two cases where the limits are reversed in either of the two cases, basically you'll get the same answer for both of these questions, but one will be negative and one will be positive. Likewise, down here, it is not the case, or rather it is the case that since your limits go from 2 to 3 here, and then from 3 to 5 here, that you'll get the same answers if you did it from 2 all the way through to 5 here. If you actually went through the work of doing those, you would get them right. So let's just take a minute and just kind of observe that. So if you did this work, okay, and you did the integral of x squared, whatever that is, okay, let's say it's something of x, right? By the way, what would it be? It would be x cubed over 3. If you evaluated that at 4 and 4, then what would happen is you would do 64 thirds minus 64 thirds, and guess what you get? 0. Now, the point of this is I want you to believe from now on, whenever you see an integral that has the same limits, the answer is certainly always 0, and there's no reason to do any work because if you're just going to subtract the same number from itself. Likewise, in this case, 3x squared, if you did this question, 3x squared, the answer to that is actually x cubed. And if you evaluate x cubed from 4 to 2, you would get 64 minus 8, which is 56. But if you did the same thing, but instead did it from 2 to 4, you would be thinking about 8 minus 56, which is, 8 minus 64, which is negative 56. And the point we're trying to make is if your limits are out of order, you can expect your answer to be negative. Often, your limits have the highest number on top and the smallest number on bottom, and you're supposed to take the top higher number, plug it in, and take the smaller lower number and subtract it out of the larger quantity you got from the top. Whenever you see strange theoretical cases of integrals where the top limit is lesser than the bottom limit, you should expect to get a negative answer. But remember, if you get the negative answer, it might just mean that you just did them backwards in some way. And when you subtract, if you subtract in the reverse way, you always get the same answer, but just negative. So that might come up in your studies, and just be wary of that, okay? There's also this idea that if you are doing two integrals, that you could put them together into one integral, and that one we talked about here. I just want to mention. Right, that if you go from 2 to 3 to 3 to 5, it's the same as 2 to 5. All right. Carrying on, there are a couple of little more examples. This is the idea of area under the curve that I was explaining to you. If you know the limits, you can act like the limits are vertical lines, like we did with our x cubed plus 4 function, and then think about that shaded blue area there, whatever function that is. If you integrate it and plug the numbers in, you'll get it. So let's say that this is some strange function like y equals x to the 4th minus 1, or something like that. Whatever that's going to be, if you integrate that and you use this number and this number as the limits, like you see here, then it will tell you that shaded area underneath. And that is perhaps the most important application of the fundamental theorem of calculus, is that it represents the area under a curve bound by the two limits, the curve itself and the x-axis. Okay, so we got two more examples, and both of these examples are applications examples. And in these applications examples, we have the specific case of apply limits and the fundamental theorem of calculus. So for part 6, it says, suppose that money flows continuously into a slot machine at a casino and grows at a rate given by the formula you see here. And we have a formula where t is the time in hours and 0 less than t less than 10. That means nt goes from 0 to 10. That's what that means. Can we just reiterate that for a minute? Because that's so easy to make a mistake with, friends. This expression means go from 0 to 10 for the letter t. Now, find the total amount that accumulates in the machine during the 10-hour period if no money is paid out. So the way we're going to do this is we're going to integrate that function, and we're going to make the limits 10 and 0. It's going to look like this. All right. And when we do this, we're going to apply all the rules we already learned. Fortunately, we already know the rule of e. That's easy for us. The integral of e to the x is just e to the x. So let's go in. I would start by taking out the 100. It is a coefficient. And again, you don't have to write the limits. I don't know why I wrote them that time, but I'm not going to write them the rest of the times. I almost always don't. I just wait until I'm at the end of them. I just evaluate. But anyway, that's the integral, right? The 100 should not be there, by the way. I took it out. Sorry about that. And now I'm going to let u equal this quantity. That implies that du equals 0.1 dt. Now, I don't have 0.1 dt, but I do have dt. So what I'd like to do is solve this for dt. So if I divide by 0.1, that's the same as writing 10 du. If you get your calculator out and do 1 divided by 0.1, it will give you 10. 0.1 is 1/10. The reciprocal of it is 10. Anyway, you want to look good at dt equals 10 du. That's why my new statement reads 100 integral of e to the, now 0.1 t is u, and dt is 10 du. I can use the constant rule once again and pull the 10 out now. 10 times 100 makes 1,000. And now, last but not least, let's integrate e to the u. And when you integrate e to the u, you get e to the u. Last but not least, u is the expression 0.1 t. So this has now just become 1,000 e to the 0.1 t. That's your solution for the integral. But now we have to use the fundamental theorem of calculus and evaluate it at the limits 10 and 0. So when you put a 10 in there for t, it becomes 1,000 e to the 1. When you put a 0 in there, it becomes 1,000 e to the 0. Now, what is e to the 1? We can use our calculator to get that. Let me show you how to do that. On my calculator, and I'm going to ask you to kind of look closely at it with me, there is a button there. It's very close to, it's hard to see it, but see the natural log button right there? Natural log. Above it is e to the x. And you probably have a similar situation on your phone or on your calculator. But basically, the easiest way to find e to the e itself is to put in a 1 and get that function, which means do second and that button. That's e right there, 2.718. So if I do 1,000 times that, it equals that figure. What is e to the 0? E to the 0, by the way, anything to the 0 is 1, right? So this is now minus 1,000. Let's do minus 1,000. And the solution is 1718.28. And that is dollars because this is a slot machine, right? Yeah, all right. So I'm gonna leave this up here so we can look at it. So I hope that was clear. As you can see, it's very complicated, but if you're really on your toes with your algebra and all the things associated with the distributive property and multiplication and all that other good stuff, then you'll be just fine. But it is a matter of paying very, very close attention to the detail. Right. We do have one more question. That's another application I'd like to focus on with you, and then we'll talk a little bit about exam 3, and then we'll dismiss for the day and for the entire term. Wouldn't that be wonderful? Here we go. The last thing is product life. It says, suppose the probability density function for the life of a computer or component is given here, and we have an expression for f of x, and we're telling you x is greater than or equal to 0. Is the number of years the component is in use. Find the probability that the component will last between 3 and 5 years. So what you're going to do here, since we're in the mood of applications on the fundamental theorem, is take the integral of this expression here and make this your limits and see what you get, right? What does that look like? It looks like this. So we would take that expression and we would use 3 and 5 like so. All right, let's get an answer. First, I'm going to apply, again, the coefficient rule and pull the 0.10 out. Next, I'm going to apply u substitution and let u equal the exponent of e here. So I'm going to have, and I'll put it up here this time, u equals negative 0.10x. That means that du equals negative 0.10 dx. Now I don't have, I do, I have 0.10 dx actually right here. Maybe I don't need to take it out. That's cool. I could just put it back in, but don't forget it's negative. So why don't we make this negative du equals 0.10 dx. That way when I take this out and this out, I make sure I include negative du for that. So it looks like this now, equals e to the u times negative du. And if I make that negative 1, I can pull it out, making it negative, the integral of e to the u du. And now the million-dollar question, what is the integral of e to the u du? The answer is e to the u, right? Don't forget that negative, that pesky negative is chasing you. Don't let it get out of the way. What is u? U is negative 0.10x. So this has just become negative e to the negative 0.10x. And now I mean to evaluate it at 5 and 3. What does that look like? Well, it's going to be, and with all these negative signs, I'm going to be careful. So I'm going to use a lot of parentheses and brackets and stuff to really be very deliberate and careful with how the negatives work. First expression, I'm substituting 5, so it looks like this. Negative e to the negative 0.5. The next expression, I'm substituting in 3. So it's negative e to the negative 0.3. Okay, now I can get answers for those things using my calculator. What is e to the negative 0.5? The way I get that is I start by putting 0.5 in my calculator, making it negative, and now asking my calculator to find e to that number by going with the second function of the natural log. There it is. Note it's negative. I can change the sign right here and make it negative. That is this first bracket. I'm going to write it in red. 0.60653. Then I have a minus. And then I do it again with negative 0.3. Let's do it now with negative 0.3. 0.3, make it negative. Now find e to that with second natural log. And then make that negative. And I have negative 0.74082. 74082. Okay, last but not least, this is a plus, right? So what I could do is I could make that positive and then subtract this out and it'll give it to me. Let's do that. So I'm going to change the sign once more with this symbol right here. And now I'm going to make that positive. I'll subtract 0.60653. And I'm getting 0.13429. That is our answer. Let's open this up. Let's get this. All right, friends. Well, here's what I have to say in closing. It really has been an honor to help you learn this summer. And I genuinely appreciate all of the hard work you've done. I see it in your work and your web assign. I see it when you write your discussions. And I see it when you take your exams. When you send me emails with questions about your homework. When you come to class and pay close attention. I see your devotion, I see your work, and you deserve the high grades you're going to get. I really appreciate everything we've done together, and thank you for having this chance with me to learn this summer. I hope it was fulfilling for you as much as it was for me. Let's talk about some housekeeping and some last minute stuff. There's 2 assignments left for you. Well, there's really actually 4. There are 2 web assigns associated with this homework, and there are 2 discussion questions. But besides that, there are 2 culminating assignments. The first one is your last exam number 3. It's not a final exam, it's not cumulative, it's only on the 3rd unit, which is chapters 12.1, 12.2, 12.3, and 13.2, which is the material we reviewed yesterday and today. As usual, it will be open from 4:30 until 9 p.m. at night on Monday. I don't know why that says 6:45, that's not correct, it should be until 9 o'clock. You'll have 2 hours to complete it once you open it. Your questions will be varied from student to student and by order and values. There will be final scores and answer guides made available the next day, and it's recommended that you do exam number 3 beforehand. Your final project will be due on Wednesday, the 10th. Now, if you feel like you'd be in a better position to take your exam Wednesday instead of Monday, that's okay. Send me an email and I can arrange that for you. On Monday, if you want, I can meet with some students and go over any homework first. I'm going to let it be the way it is unless you need that help. But please reach out to me and let me know if you need that help, and then I'll be here for you on Monday at 4:30 if needed. Okay? But that's if needed. You may feel like you don't need that. If you don't, that's okay too. But let me know if you need me. I'm here to help you. All right. The other thing that's important is there is a final project, and that final project is due on Wednesday, and that's not going to change. I need for you guys to make sure you turn that in on time so that I can get my grades in on time so that we could finalize the summer term. That's all that I've got for you. It really has been a pleasure studying with you, and thank you for your attention. I'm going to end the class here, and then we'll stop the recording and open up the floor to questions for the students. Everyone have a great day, and thanks for your attention.